All right, now you're going to start getting flashbacks. So now we're going to do different KSP calculations, and we're going to go through the different types. There is 1, 2, 3, 4. There are only 4 types of equations that we're going to do with KSP. So before we start this one, which is calculating KSP with given concentrations at equilibrium, very similar to type 1 in unit 2, I want to review a little bit of terminology with you. The first one is the word solubility. Solubility is the amount of substance that dissolves to form a saturated solution. Right? So that's a lot of words. So when we've talked about solubility, we've got things that are soluble, we have things that have low solubility, negligible solubility, but solubility of itself is just the amount of substance that dissolves. And then from there you could decide, is it soluble, does it have low solubility, or does it have negligible solubility? But things will dissolve to form a saturated solution. A saturated solution is a solution that's containing as many ions as it possibly can contain. So that'll mean that it's at equilibrium and it's fully dissolved, and you're now starting to, dissolve and precipitate and dissolve, or what's another word for that? Dissociate, precipitate, and so on and so forth. When you're asked to calculate solubility, the units for solubility are grams per liter or moles per liter. Now, if they specifically want molar solubility, they can actually ask for it. So instead of just using the word solubility, they can use the word molar solubility, and this will be the equilibrium concentration of a dissolved substance in moles per liter. So it's the solubility in moles per liter, right? It's no different. It'll be the number of moles that dissolve in 1 liter of a solution. And then lastly, just that term solubility product, which is obtained by multiplying the equilibrium ion concentrations together in a saturated solution, meaning holding as much as it can, and there are no units. So we've got solubility and molar solubility that are the same but different, right? So molar solubility is specifically moles per liter, and then we've got solubility product constant, which has no units. All right, now, just a little note. Your calculator may need to be set up in scientific mode for some of these problems. It's a unique thing that happens, and it happens in this very first question, and I feel like I could have just left it out, but I feel like it's important to know. So if you're getting any answers different than mine in the answer key, it could be, and if you're off by like 1 decimal place, it could be that your calculator isn't showing enough precision, and so you don't know that you should round. Let's look at an example of this. So let's just set this up and then we'll determine if you need to or not. A solution in equilibrium with a precipitate of barium fluoride contains 4.59 times 10 to the negative 2 molar, or moles per liter, of barium, and 2.00 times 10 to the negative 3 moles per liter of fluoride. What would be the KSP for barium fluoride? So the first thing we would start with is writing the dissociation equation for barium fluoride. I often find when I do these, I know that it's a dissociation, so I know it's a solid going to aqueous ions. I start leaving off the states. If this was a test, I wouldn't, but especially in my homework, I find writing states really tedious, so I stop. But I'm going to for this first one, but just saying that I might stop after this one. Then I'm going to write my KSP expression. So my KSP at equilibrium is going to be equal to the barium ions times the fluoride ions squared. Now, they gave me the concentration of barium at equilibrium. So I've got a saturated solution and I'm at equilibrium. And my concentration of barium is 4.59 times 10 to the negative 2. And my concentration of fluoride ions is 2.00 times 10 to the negative 3. And then that one's going to be squared. Okay, so let's go plug this into our calculator. Now, I'm curious how my calculator is going to handle this. Okay, so I'm going to type in 4.59. This is the downside of only having these calculators. This calculator doesn't even have times 10 to the... Really? I don't have an EXP button. So what I'm looking for here is my EXP button to tell my calculator that this is all one number. Unless I'm being absolutely blind, this calculator doesn't have one. Oh, that's too bad. Okay, I just went and found a different calculator. So what I wanted to do, I want to do one that has a times 10 to the, or an EE button. So this calculator has the times 10 to the. So I'm going to enter this as 4.59 times 10 to the, and then it writes an E. So maybe your calculator has EXP or EE, something along those lines. And then I'm going to put in -2. I'm not going to use my subtraction sign, right? I'm going to put in my -2. And then I'm going to multiply that by 2 times 10 to the -3. Now, because I've used my EE button, or my 10 times 10 to the button, I can just simply put that as squared, and it knows to square the whole thing, right? It knows 2 times 10 to the -3 is a number that can't be separated. So this is not -3 squared. This is 2 times 10 to the -3. If you don't have an EE or a times 10 to the button, make sure you're good at putting brackets in. So if you're not sure, you would want to put brackets around this to tell your calculator for sure that that is one number. You know, if you're being really careful, you could put a bracket in here, and then you could tell that it's a number. But you'll notice that my answer is not changing because I know how my calculator works. And my calculator works that the EE button or the times 10 to the button tells my calculator that's all one number. Now, what I'm noticing is that this calculator is giving me a different answer than my handheld calculator. If I plug this into my handheld calculator, 4.59 EXP for my calculator, -2, times 2 EXP -3 squared equals, my calculator gives me 0.000000183. And so I would answer 1.83 if I was doing 3 sig figs times 10 to the -7. But unfortunately, that's actually incorrect. Now, I'm not going to be this picky on a test. I'll try not to make any of them come out as this. But when you have numbers that are kind of on this borderline in length, what you want to do is get your calculator to show you more so that you know what to round to. So the rule of thumb is that if the number that reaches the end of the calculator is the one that you're supposed to round, you need to show more digits. Now, this online calculator put a 6 after it, so I know that this is 1.84 times 10 to the -7, but yours doesn't show that. So what you would do is you would set up your calculator to scientific mode. Now, depending upon the calculator, some calculators you hit mode, some calculators you hit setup. So for my calculator, I have to hit setup, and then a button that comes up is FSE, or a code. So for me, it's number 1. And then if I choose 1 again, I can choose psi. So the key thing is you're going to hit either mode or setup, and you're going to look for a way to set your calculator into scientific notation mode. So if I hit 1, now it's going to give everything in scientific notation. So 4.59 EXP -2 times 2 EXP -3 squared, and now it gives me 1.836 times 10 to the -7 as my answer, so I can round it to 1.84. So sometimes when you're talking about really little numbers all the time, it's nice to just leave your calculator in the scientific mode. I'm not saying this as like a thing that's going to be a big thing in this course and you have to be really careful. What I want you to be careful with is that if that last number that you're writing down needs to be rounded, there's a chance your calculator hasn't put the next number down, which would make you round up. So if in your homework you find that you're off by 1 decimal place, that may be the case. And a simple fix for this is just to put your calculator in scientific mode. Now, if you want to switch your calculator back, you know, for me, I hit setup, I hit that FSE again, and then the weird thing is that what I want to put it in doesn't show. I actually have to go over to number 3, which is putting it in normal mode. So up to you, but it is good to have the ability to switch between scientific notation and just normal mode in your calculator. Okay, so what else could they ask you? Well, at a certain temperature, the solubility of scandium carbonate is 7.5 times 10 to the -5. Calculate KSP. So what's happening here? Well, you've got this scandium carbonate, which would be in equilibrium with its ions, which would be scandium 3+, and carbonate 2 minus, and you would have 2 scandiums and 3 carbonates. And they're telling you that the solubility of scandium carbonate is 7.5. That's this value here. So there's a reason we did net ionic equations and our mole to mole ratios in another lesson. If my molarity of scandium carbonate is 7.5 times 10 to the negative 5, then the concentration of the scandium ions would be twice that. So 7.5 times 10 to the negative 5 times 2, which would be 1.5 times 10 to the negative 4, or 0.00015, whatever you're more comfortable with. And then the concentration of carbonate would be that same number, 7.5 times 10 to the negative 5 times 3, which would be 2.25. Remember, we're just keeping 2 sig figs, but we don't want to round, times 10 to the negative 4. So now to calculate KSP, I'm going to write down my KSP equation, which is going to be the scandium squared times the concentration of carbonate cubed. So in here, I'm going to put 1.5 times 10 to the negative 4 squared times 2.25 times 10 to the negative 4 cubed. All right. You should get to 2 sig figs. We are going to get 2.6 times 10 to the negative 19 and no units on KSP, right? So concentration had units. This does not. All right, next part. There's a reason why at the beginning of this lesson I reviewed for you the words solubility and molar solubility. So this is telling me that the solubility of iron 2 hydroxide is 1.5 times 10 to the negative 3 grams per liter. And we want to calculate KSP. KSP is always found from molar solubility or concentration. So what we would have to do is figure out what this would be in moles per liter. So iron 2 hydroxide would be iron hydroxide, right? And that is going to go down to iron 2 plus and 2 hydroxides. And the first thing we have to do is find the concentration of, or not really the concentration, the molar solubility of iron 2 hydroxide. So we've got 1.5 times 10 to the negative 3 grams per liter of the iron hydroxide. Now, iron hydroxide would have a molar mass of what? Well, it is 1 iron, which is 55.85. It is 2 oxygens, which are 16 each. And it is 2 hydrogens, which are 1.008 each. So the molar mass of iron hydroxide is 89.866. Oh, man. I didn't give myself enough room. Anyway, I can fit it in. So then 1 mole of the iron hydroxide weighs 89.866 grams. So then the molarity, or the moles per liter, would be 1.5 times 10 to the negative 3 divided by, I'm just going to hit answer, and I get 1.6691 times 10 to the negative 5 moles per liter, or molarity, right? So solubility and molarity, it's the same. It's almost like we now have a purpose of why it's moles per liter. Like, why have we been talking about liters all the time? Oh, it's the solubility of your substance. Okay, so now what we're going to do is find the concentration of iron, which is just going to be that same one. And it would be a good idea to save this maybe as A. So I'm going to store as A. And then I'm going to take that same concentration and multiply it by 2. So the concentration of hydroxide is going to be 2 times that 1.6691. So 2, which gives me 3.3383 times 10 to the negative 5. And I'm going to store that as B so that I don't have to type these things in again. And I'm keeping them as exact as I can. And now I'm going to find KSP. So KSP is going to equal the concentration of iron times the concentration of hydroxide squared, which is going to give me that answer A, I'm just going to be lazy, times the answer of B squared. So in my calculator, I'm going to hit recall A times recall B squared equals, and then I'm going to answer the correct number of sig figs. So 2 sig figs is going to give me 1.9 times 10 to the negative 14. And again, no units on KSP. All right, hopefully you got the same as me. All right, we've got one more example here. So if you're feeling it, give this one a go on your own. If you're not, I can walk you through it. Okay, so for this one, we have 6.60 grams of the manganese fluoride will dissolve in 1 liter of solution at 25 degrees Celsius. Calculate the value of KSP for manganese fluoride at 25 degrees Celsius. So for this one, we have manganese fluoride will dissociate into manganese ions and fluoride ions. Well, 2 of them. They've given us that 6.60 grams of the manganese fluoride will dissolve in 1 liter of solution. So my solubility will be 6.60 grams per liter. So I want to take the 6.60 grams of manganese fluoride and convert it to moles. So 1 mole of manganese fluoride, you know when you have a fear that you're saying this wrong? I'm pretty sure it's manganese. Now I'm doubting myself, right? Weighs how much? Well, MnF2 is made up of 1 Mn, which you look up on your periodic table, and it has a molar mass of 54.94. And then 2 fluorines, which each weigh 19, gives you a total molar mass of 92.94 grams per mole. So 1 mole weighs 92.94 grams. And so I'd plug into my calculator 6.60 or 6.6 divided by 92.94, which is 0.07101 ... moles per liter. Then what we'd want to do is find the concentration of the manganese, which is going to be equal, because it's in a 1-to-1 ratio. So it's going to be this 0.07101 moles per liter, and I would save this as A in my calculator. And then we would do the same thing for the fluoride, but it's going to be 2 times that answer. So I'm going to take this and I'm going to store it as A, and then I'm going to times it by 2, and I end up with 0.142027 moles per liter, and I'm going to store this as B. So then if I'm calculating KSP, KSP is going to equal the concentration of manganese times the concentration of fluoride squared. So I'm going to take that answer A and I'm going to times it by the answer B squared, which is going to give me, depends on if you want scientific notation or not, 0.00, and then how many sig figs are we keeping? We can do 3. This one didn't put it as numbers, so I'm just not going to count it. I'm going to say that we can do it as 3. So we're going to put 0.00143, or we can write that in scientific notation and have 1.43 times 10 to the negative 3 as my KSP. Awesome. All right, go and practice some of the type 1 questions.